Welcome to Cindy Mix Online Tutorials. On this episode, we'll be discussing on some more problem-solving techniques on thermodynamics. Welcome back. Now we have a question before us. I'll be reading it out and we're going to try to solve it. The question says a quantity of air occupying 0.14 dm cube at 9.6 bar and 371 degrees Celsius in a piston cylinder assembly is heated during a constant volume process until the pressure reaches 41.4 bar. The air is then expanded adiabatically and polytropically with index of expansion being 1.4 to a pressure of 2.76 bar and temperature of 984 degrees Celsius. Now, the assumption says that we should assume that the air behaves like an ideal gas and kinetic and potential energy effects are negligible. Now, what we have to calculate is to calculate the temperature of the air at the end of the heating process in degrees Celsius. And 2, we have to calculate the heat transfer during each process. And 3, we have to calculate the total work done produced for the two processes in kilojoules. So now the assumption, the constants were given for air. Cv is equal to 0.7165 kilojoule per kilogram Kelvin, and Cp, which is 1.0035 kilojoule per kilogram Kelvin, and R, which is 0.287 kilojoule per kilogram Kelvin. So now let's solve. So now the first thing we need to do is to make some assumptions. Let us make some assumptions. The number one assumption that we make is that process 1 to 2 is a constant volume process. Process 1 to 2 is a constant volume process. And 2, process 2 to 3 is an adiabatic. You can say process 2 to 3 is an adiabatic process. And what that means is that Q2 is equal to what? 0. Q2 is equal 0. So first you should understand that. That's our first assumption for. And the third assumption that we have is that the gas is an ideal one. That is a very, very crucial assumption. That the gas is an ideal one. That goes a long way in this solving problem we're about to solve. And number 4 one, we say potential and kinetic energy effects are neglected. So now we know for process 1 to 2, we know for process 1 to 2 that V1 is equal to what? V2, since it's a constant what? Volume process. And our T1 is equal to 371. And our P1 is equal to 9.65 bar. And we know our V1 is equal to 0.14 dm cube. Our V1 equal to 0.14 dm cube. And our P2, I suggest you get a pen and a notepad there to get down all these values, because our body is not that quite long, so we can get all of them in motion. So we have 41.4 bar. That is for process 1 to 2. All these are for process 1 to 2. Now for process 2 to 3, we know our V3 is equal to X. We don't know what our V3 is. And our P3 is equal to 2.76 bar. And our T3 is equal to 984 degrees in Celsius. Now to get our T2, we've gotten our T1. We've not gotten our T2. Let me add that to be X. Now to get our T2, if you remember, we can either use this relation. We can either use this relation. We can either use this relation, or we can use this relation. If you remember, PV equal T, which is a constant. So now let us say now that we make V subject of formula. We can say T1 over P1 equal T2 over P2 when V is made subject of formula there. So our T2 becomes our T1 times P2, which is equal to 6. Now I'm going to be converting them to Kelvin, which is 644 Kelvin multiplied by P2, which is 41.4 bar, over our P1, which is 9.65. So our T2 becomes 2489.86 degree Celsius. Our T2 becomes 2486.86 degrees Celsius. Now we've gotten our temperature. Now our T2, that is our first aim for this exercise. Now the second one requires that we get our heat transfer during each process. That is the process process 1 to 2, we get our heat transfer. Process 2 to 3, we get our heat transfer. Now for process 1 to 2, if you remember the general first law where we said Q is equal to W plus change in U. But now I want to get Q1 to 2. So we say Q1 to 2 equals work done from 1 to 2 equals this to 1 to 2. And remember we said process 1 to 2 is a constant volume process. That is to say, that means this work done will be equal to 0, because once we have a constant volume, that is to say when we have V1 equal V2, our work done is going to be equal to 0, because our work done can be said equal to V1 minus V2. But when V1 minus V2 is the same, this is equal to 0, so 0 times anything here is what? 0. So our work done is 0. So our heat from process 1 to 2, that what we're about to get now, that is going to be equal to the change in internal energy. And we also know that change in internal energy is also equal to mCV open bracket T2 minus T1. Now to get our M, recall that we have something like this: PV equals to M arrow T. All we are just trying to get is to just look for formulas. That is just the ideal of this thermodynamics. Look for formulas that we enter into what you're about to do. This change in U, if we were being given X, that is to say the quality, we would have used U equal to UF plus X UFG. That's if we were given X. Or do you understand what I'm saying? So we have to just look, open your eyes, learn formulas. There's no easy way about going all this. There's no easy way about this. You just have to sit down and learn it. You just have to sit down and learn it. So because we have PV equals M arrow T. So now we want to get our M. You make M, so the formula, you say this arrow T. So our M be give us, let us say this is P1, V1, T1. So now our P1 gives us 9.65 times V1, which is 0.14, over ROT, which is 0.287 times 644. This is in Kelvin now. So now we're going to times it. Now, if we're timing it with this 2 to make it in kilojoules, in kilogram, because when we calculate all of this, it's going to give us in grams. So we're timing it times 10 to the power 2 to give us in gram. So our M becomes 0.731 kilogram. We've got our M over to be 0.731 kilogram. So now what we have to do is impute it back into the equation there. Now I've wiped up the board. So now imputing that into our equation, we become MCV, which and our M becomes 0.731 kilograms. Now I want to put all my formulas in now so we can see how to get the base formula for our Q1 to 2. We have MCV. Now for the CV we have 1. Now let's calculate. Kilojoule per kilogram Kelvin. T2 minus T1. For T2 we have 2.86 minus 644, all in Kelvin. So now Kelvin cancels out Kelvin. Kilojoule cancels out kilojoules. So we are kilogram cancels out kilogram. So we are left with what? Kilojoules. So you see how it all goes. You see how to get the base currency there. So you have 1109.78 kilojoules. So now we've gotten our Q1 to 2 to be 1109.78 kilojoules. So now to get the C part of our question, the C part says we should calculate the total work done. The C part says to calculate total work done, which is work done from process 1 to 2 plus work done from process 2 to 3. So now work done from process 1 to 2, we've already know needs to be what? 0 to 2. To get now the work done from process 2 to 3 is what we are about to derive here. So work done from process 2 to 3 gives us P3 minus times P and V3 more minus P2 V2 or -1 minus N. Now P3 gives us, let me write it here. So now P3 gives us 0.73. Sorry, we don't know what P3 is. Oh yeah, we know what P3 is, but we don't know what our V3 is, and there's no information to provide what V3 is. There's no information to provide what V3 is. So now, if we look at this, we don't know what V3 is, but we know what P3 is, we know what P2, we know what V2 is, but we don't know what V3 is. We also know that work done is also equal to T3 minus T2 over 1 minus N. Do you remember this formula? We know MR is equal to open bracket T3 minus T2. We have M, we have R, we have T3, we have T2. So always we can always impute that to get our answer. So our M becomes 0.731 kilogram times R becomes 0.287 kilo. Let me get back the kilojoules per kilogram Kelvin multiplied by T3, which gives us 1257 minus 2762.80. Yeah. So now to get our N minus N, which becomes 1.4. Do you remember how this T3 was gotten? Remember, we said, if you remember when we were given the values, when I asked you to write the values down, our T3 there was 984 degrees Celsius. But when we plus it with 273.17 Kelvin, we get it to be in this form here. So our work done, let me write it here. So our work done for this process 2 to 3 becomes 789.81 kilojoules. So the kilogram cancels kilogram, Kelvin cancels Kelvin, so kilojoule is left. So with that being said, I'll be drawing the curtain here, and I'm going to now lesson 2. We're also going to be discussing on a more cogent and a more strong, or will I say more conc question on thermodynamics. I'll be dropping the comprehension down now, and I would like you to try them out and see how strong you are, or how strong your mental capacity is in solving some of these thermodynamic questions. Bye bye, have a wonderful day.